discussion, during the quiz paper discussion, you told that mock unit will be released with week 7.
It is not yet released.
No.
Let me tell you again right now.
What, sir?
I will again inform them to release the mock unit.
Okay.
Okay, let's see my screen, Kaushik.
Sir, your voice is low.
Yeah, are you able to see my screen?
Yes, sir.
Okay, super. So basically, it's going to be a one-on-one session. Okay.
Yes.
So let's start off. Today we'll be discussing about week 6, where we actually start off with modeling. Okay, week 5 and week 6. So both together, which is going to be focusing on regression. Right? So we have something known as the simple linear regression and the multiple linear regression. These are the two topics in weeks 5 and week 6. Okay. So the first thing, what does regression mean? Regression means association. Right? So I'm going to find the association between variables. When I'm doing this association, I'm going to model it as a linear relationship. Right? So I'm going to do a regression. And that regression is going to have an association which is linear in nature. And this linear relationship is either single or multiple. Right? So SLR. So what does this, sorry, simple or multiple? Simple linear regression or multiple linear regression?
So basically, in simple linear regression, we have only 1 or 2 variables. But in
Not 1 or 2. You have only 1.
1, yes.
Y is going to be beta naught plus
Beta
beta
1x.
1 x1 plus epsilon. This is going to be your SLR. Whereas in your MLR, it's going to be y is equal to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth, plus beta k xk plus
Plus
epsilon. That is going to be your MLR. Okay. So in a lot of other courses, basically your statistics, your MLT or MLP, wherever, they will cover a lot of topics in this aspect: simple linear regression, multiple linear regression. Our focus is not going to be on this. What I want to do is I want to link this topic to something known as ANOVA. What is ANOVA?
Sir, it's used in Excel for descriptive statistics.
It is not only used in Excel, uses ANOVA. What is the concept of ANOVA? What is the full form for ANOVA, first and foremost? AN is one word, O is a word, then VA is another word. So what is
Analysis of variance.
exactly? So it is analysis of variance. This is what is ANOVA. So what we are doing, we are going to analyze variance. Now tell me, when you build an ANOVA table in Excel, what are the 3 rows of that table? If you are creating an ANOVA table, there will be 3 rows. What are they? What are they titled?
R square,
No, that is the summary statistic. The ANOVA table will have 3 rows.
slope, intercept, and that one.
No, that will be the table below this. Below this, there will be another table, which is different. This is the ANOVA table. On top of it,
Regression, residual, regression,
it will be known as
regression, residual, and total.
regression, residual, and
Total.
total. This is your 3 rows of your ANOVA table, right? You usually call this referred to as R. This is E, error, and total is T. Usual notations, right? So those are the rows. What are the columns?
DF,
Okay. What is DF?
degree of freedom.
Degrees of freedom. Super. Next.
Sum of squared.
Okay, you have something known as SS. Okay. Next.
Then is MS, mean squared.
Mean sum of squares. Okay.
Then F value.
Then you have the F value.
And then the significance F value.
The significance, which is basically the P value.
P value, correct.
The last column is the P value. Okay. So this is your ANOVA table. Now this is known as analysis of variance, right? So what are you analyzing? You're analyzing of the total variance that is available in the data, how much is captured by the regression and how much is sitting in the residuals. So I have a data set, I have X, I have Y. For simplicity, let's just assume there's only one X. And the model you have built is Y is equal to, or Y is equal to beta naught plus beta 1 X plus epsilon. So this is the model that you have built. This guy is going to give you a prediction. Those are your data points. This portion of the model is going to give you a prediction. And for every predicted point, right, there is going to be an error. That is that. That is your epsilon. So for every predicted point, there is going to be a prediction y hat plus some epsilon error. So the total variability in the data set is split between the predicted variability and the random variability, which is epsilon. This is known as analysis of variance. So if you build a model which has a significant capture of variability by the regression and very little capture of variability of the residuals, then you have built a good model, right? So that is what it means. I'll come to the degrees of freedom in a minute. So how do you find the sum of squares? What is the total spread because of the regression? That is the question, right? So, for that, I have a data set y, which has y1, y2, y3 up to yn. And for this, I have an x1, which is going to be x1, x2, x3 up to xn, right? I make a prediction y hat, y1 hat, y2 hat, y3 hat, yn hat. How is this got? This is got as beta naught plus beta 1 x1, right? So that will give me yi hat is going to be equal to xi. I get these predicted values. From the data set, I can find out the mean y bar. That is going to be my mean value. What is spread? Spread is around this mean value. So the total variability in my data set, which is SST, right? That total variability, SST, is going to be yi minus y bar the whole squared, right? That is the total spread of my of my y. The total fluctuation of my y values around the mean value. I take every point, subtract it with the mean, sum this up for all the data points. That will give me my SST. The total spread of my data around the average value. Okay, we have got that. Now you have fit a model and you have found the yi bars, right? Or yi hats. So the variability captured by that is known as SSR, which is the regression. So SSR is equal to summation over I is equal to 1 to n. This yi gets replaced by yi hat. The yi bar is the same. As compared to my actual mean, how much am I fluctuating because of this predicted value? That is my SSR, sum of squares, that is accounted for by the regression model, which is this guy for the regression term. And what is SSE? Yes, Kaushik.
So, like, can you please explain how y hat value is calculated once again?
Y hat is your predicted value.
Oh, that beta naught plus beta
Y
1x.
hat is equal to beta naught plus beta 1 xi. That is your yi hat. It's a predicted value.
Okay, got it, sir.
Right? So with that, you get your SSR, which is the regression. Now, when you fit a model, the SST must be spread between the SSR and the SSE only. So the sum of squared total is equal to sum of squared regression plus sum of squared error. So SSE is equal to SST minus SSR. So that is the remaining variability that is sitting there. You can find it like this, or you can always find SSE as summation I is equal to 1 to n yi minus yi hat the whole squared. This is your SSE, which is nothing but take all the errors at every point, your errors at a point is going to be E1 or E2, E1, epsilon 1, epsilon 2, epsilon 3, up to epsilon n, where epsilon I is nothing but yi minus yi hat. Actual minus predicted. Okay. So you can get the residual variability either by taking the difference between actual minus predicted the whole square, sum it up, or that is always going to add up to the total. So SST is equal to SSR plus SSE. So the variability must either be because of the error or because of my model. So sum that up and get the values appropriately. So this is known as the sum of squares, and this is why it is known as ANOVA, analysis of variance, because you are looking at this variance term, the sum of squares term. In a nutshell, it is very similar to variance. No? The only difference is you are not taking the 1 by n. Instead of dividing it by the number of data points, taking the thing, you are doing as yi minus y bar the whole squared. So that is why it is known as the analysis of variance. You are analyzing how the variance is split between the regression, residuals, and total. All of you with me so far? Okay. So now, in this table, regression degrees of freedom refers to the number of betas associated with the independent variables, right? So for an SLR, since you are only having one independent variable x1, which implies there's only going to be one coefficient v1, the regression degrees of freedom will be 1. Because that is only one point that you will have to find out, one beta that you will have to find out, which will hold the model. But if there are multiple x's, if it was an MLR, where you had x1, x2, so on, up to xk, you basically have to find beta 1, beta 2, up to beta k. Then there is k degrees of freedom, right? So in general, what we write is the degrees of freedom for a regression is going to be k, which is the number of predictors. Which is nothing but your independent variable x's. Those will be the number of degrees of freedom in which direction the model can move. Right? So that is regression. The total is nothing but n minus 1. Why? Because I have n data points. Of that, one data point is required for calculating the beta 0. So there is n minus 1 degrees of freedom for the total variability to move. In fact, look at this guy. For the total, for calculating SST, I need to know the y bar, for which I must do a computation from the sample. Right? If I have to find the mean 1 by n equal to y bar, if I have n minus 1 data points, I can find the last data point. Right? So what is the mean of 1 plus 2 plus 3 by 3? Right? So that is 6 by 3, that is 2. Now I am telling you the mean is going to be 2. I have told you one value is 1, the other value is 2. And there are 3 data points. Then obviously the third value must be 3. Only then this summation will be equal to 2. So if n minus 1 data points are fixed, the last data point can automatically be found. So the number of degrees of freedom is n minus 1. Okay, got it?
Yes, sir.
Okay, even if you don't get it, that is still fine, but I'm just trying to tell you. Okay, and the total must always be these two. So this guy is n minus k minus 1. You'll always see in the columns of these guys, the regression plus residual will always be equal to total, right? So this is this. I want the mean sum of squares. So what do? I just take the SSR divided by its degrees of freedom, SSE divided by its degrees of freedom, and SST divided by its degrees of freedom. That gives me the mean sum of squares. Most cases, we will not compute this. This is not of interest for us. We'll only be working with these two, which is SSR and SSE. So I want to compute my F statistic. What is my F statistic? Can someone tell me?
So it's SSR times
MSR by MSE. That is all. SSR times n minus k minus 1 divided by SSE times k is basically going to be MSR by MSE. So that is your F statistic. And then correspondingly, you find the p-value from the F statistic table, where you need 2 degrees of freedom, rho 1 and rho 2. Rho 1 is going to be k, rho 2 is going to be n minus k minus 1. That is all. Fine? Yes, no?
so F value will be same for both regression and residual. MSR divided by MSC.
Pardon me? MSR, F statistic will be?
So like for as sum of squared and mean squared, we are calculating regression and residual separately. But for F value, we have one value or we have to
Only
calculate
one value. Only one value.
Okay.
Because that is sum of, that is, this MSR, no? This is MSR. This is MSE. That is your F value.
Okay.
Correct? Super. Now tell me, what does this F value signify? What you are doing an analysis of variance, correct? So you are doing an analysis of variance. You are analyzing this variance between regression and residual. And you are doing some hypothesis test here because you are doing an F test. This is basically an F test. And that is why you are trying to find the p-value, the significance value. So what is this hypothesis test? What is the null hypothesis? What is the alternative hypothesis?
Sir, null is accept T, no, reject T, null, do not
That
reject
is
T.
the conclusion. If you are going to reject the null or not reject the null, you must tell me what is the null now. So what is the null? What is the null hypothesis? You do all of this for the model. So the null hypothesis is that the model is insignificant. That is your null. And the alternative is that it is significant.
It is significant.
So what does the model is insignificant indicate? It says beta 0 equal to beta 1 equal to beta 2 equal to whatever equal to beta k. All of these are 0. I am fitting a regression model y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus so on beta k xk plus epsilon. This is telling all of these values are going to be 0. So y is equal to epsilon. Y is completely a random entity. You have not built anything that is going to help you predict. That is your null hypothesis. And the alternative says, no, no. You have some beta. You don't know which one, but you have some beta which is significant. You have some beta which is not equal to 0. That is your alternative, right? So you find the so you solve and find the f value and the p value corresponding to it. So now, how should the f be? Should f be large or small for you to reject h naught? So there are two cases. My f can be large. This f statistic, f value can be large, or f value can be small. Based on this, you must either reject the null or not reject the null. How should the f value be? Should it be large or small?
So for rejecting the H naught, alpha value should be less than F value, that is P value.
Alpha is okay. This is f statistic. No, alpha is p value. I'm talking about f statistic. Based on the f statistic value, you will then find the p value. And based on the p value, you will say how large is large, and you will either reject the null or not reject the null. But even before that, what values of f will lead to rejecting the null? Will it be very large
Large,
values or very small values?
large.
Why?
Sir, because at the end we are seeing that the P value or alpha value should be less than F value when we will reject. So basically F value should be large so that we can reject it without seeing alpha value.
Okay. But even more intuitive, look, we are doing an analysis of variance. The variance can only be split between the regression and the residual. Nowhere else can the variance go. So look at the numerator. Numerator is what? Average regression variance. Somewhat, no? 1 by, instead of 1 by n, you're putting 1 by k. Denominator is what? Average residual variance. So when the error variance comes down, automatically MSR goes up, which means
Yes,
what?
correct.
There will be a large numerator, small denominator. The fraction will be very large. And when the fraction is very large, the f value is basically very large. So when you get a very large f value, you will tend to reject the null hypothesis, which says, and you will get a very large f value only when these betas are not significant. Oh, sorry, and the betas are significant. They are not zero. They are some number. They are able to capture this predicted value that is sitting here, that is able to capture something of y. More the better. So when these betas are not equal to 0, your MSR will be very high, your MSE will be low, and hence your F statistic will be very large. When you have a very large F statistic, your P value will be very small, and hence you will reject the null hypothesis and conclude that the model is significant. But when your F statistic is very small, your P value will be very large, and hence you will not reject the null and say the model is not significant. All of you with me so far?
Yes, sir. Actually, I confused in this concept only. Now it's clear.
Ah. So this is what it means. F value, this is the importance of F value. Now comes the question, Okay, the model is significant, which means what? Beta not equal to beta of this guy. This statement, you are rejecting this statement. When you reject this statement, the next thing that comes, the next question that comes into mind is, which betas are non-zero? Because this statement says all betas are zero. And when you reject it, you could reject it even if one of them is zero or some of them are not zero, right? Even if one of them is non-zero, or if some of them are non-zero, or if all of them are non-zero, you will still end up rejecting the null hypothesis because your statement is all of them are zero. So the next question is, which betas in your model are non-zero, right? For which you take the second table. This is table 2. You take the second table. So what are the rows in the second table?
Intercept
Okay.
and the x variable.
And then you will have the x variables. You will have x1, you will have x2, so on up to xk. So how many? So the total count here would be equal to the number of betas. That is beta 0 plus beta 0, beta 1, beta 2 up to beta k. So the total number of betas in your model will be the number of rows in this table. So if you have 100 x's in your model, 101 rows will get populated in this table. This is a t-test where you will take the intercept, you will get the coefficient value. So this will be the value for beta 0. This will be the value for beta 1. This will be the value for beta 2, so on up to beta k. What is that beta value? 0.1, 1.2, 3.4, 100, 120. Whatever is the value will be the first thing that comes, the coefficient. What will be the next column? What is the next column?
Standard error.
Wonderful. What does the standard error signify?
So basically the standard error signifies what exactly the beta's value are.
Oh, that is given by this coefficient. This is the exact value. What does this guy signify? Okay, I'll give you this as homework. Check what it signifies. Or what it tells, right? What do you interpret about the standard error? That is here. The third is where the actual thing starts. It is the t value or the t statistic, which is going to be the coefficient divided by the standard error of that coefficient. That is the p-value. Once you get a statistic, you will obviously have the p-value, which will tell you whether it is significant or not significant. So, oh, sorry. You will have the p-value. P for beta 0, P for beta 1, and so on P for beta k. Now what you can do, the null hypothesis here is that beta 0 equal to 0, beta 1 equal to 1, equal to 0, beta k equal to 0. That is your null. You have a p-value. You will reject this null reject H naught if p-value is less than alpha. So reject H naught I if p-value for beta I is less than alpha. So when you reject the beta value, you will know which all betas are non-zero. So this hypothesis, you will know which betas are non-zero, or truly non-zero. Right? All of you with me so far?
So yes, and sir, you asking about the standard error. So basically, I think it's how the sample means varies from the population means.
Uh, that is a very okay, not very accurate. Because when you say sample mean, it's not only for the mean. Now here you are not doing for the mean. Here you're doing it for the beta estimate. Okay.
Okay, okay,
So
yes.
okay. So I that is not right, but I have a it's close enough, but not very accurate. Somewhat close enough, but not very accurate. Okay. Have a look at it. You can
Okay,
always
okay.
message me personally. I'll always be happy to answer you. Have a look at it.
In discourse, sir.
Yeah, yeah. In Discord, you can also send me a personal chat. That is also fine. Okay. Right. So this is the table 2. Okay. The final aspect in this topic, the final point is regarding something known as the R squared. What is R squared? What is the definition for R squared?
It's a proportion of dependent to independent variables.
Okay. Right. So this is nothing but the correct coefficient of determination, and it basically means what he says, the proportion of variability captured by the model. Proportion of variability in the independent variable y that is captured by the model, right? So this is basically R squared. So R squared is the proportion of variability that is captured by the this thing model as compared to the total variability, right? So SSR by SST is your R squared, which is going to be SST minus SSE by SST, which is going to be 1 minus SSE by SST. All of these are formulations for formulas for the same thing. Coefficient of determination of the total variability which is available. How much portion is captured by the model? Higher R squared, better the model, right? Yes, no? Yes, no, all of you with me so far?
So like I have a doubt. Like we said that higher R square is better. But
Hmm.
what if we get the lower R square, then we have to uh, re uh, rectify our
Wonderful,
model or rectify our model or
wonderful, beautiful, which was basically my next definition. This R squared will never decrease as you add variables, right? So let's say I build R squared 1, okay, or R squared A. This is for model A where I say YA is equal to Y, let me write it like this. Let's say I have model A, which is Y is equal to beta naught plus beta 1 x1 plus epsilon. This guy has R squared, which is RA. I have a model B, the same Y. The Y's are the same, but my model is beta 1 x1 plus beta 2 x2 plus epsilon, right? This will give me an R squared RB. You will see that R squared B will always be greater than R squared A. This is always the case. As you add more variables to the model, automatically the SSR will increase and hence the R squared will increase. So the question, so higher R squared better the model. There's no doubt in this statement. This statement holds true. Higher R squared better model holds true. So what does it mean? I'll just keep on adding variables and my model will become better. No, because the simpler model is always the best. You could end up adding variables which are multicollinearity. Those problems and all will come. So what you do is to see whether an incoming variable is truly contributing significantly to the model's ability to capture variance, you use something known as the adjusted R squared. And what you adjust, you just say this was your, this formula was for the R squared, right? 1 minus SSE by SST. Now what you do is, you say the adjusted R squared is going to be equal to, I will not take the SSE, but I will divide it by n minus k minus 1, divided by its degrees of freedom, divided by n minus 1, which basically translates to 1 minus SSE into n minus 1 by SST into n minus k minus 1. So what have I done? I have basically now penalized, I have penalized my model for adding more case. So the denominator will decrease, correct? N minus k minus 1 is even lower. So the denominator will decrease, which means SSE by SST on a whole, this guy will increase. So 1 minus that, on a whole, this guy will decrease. So adjusted R squared will decrease as I add more case, provided SSE is constant. But it is never constant. When you add more variables, your SSR will also change, your SSE will also change. SSR will always increase, which means SSD will always decrease. So SSD, when you add variables, SSE will decrease. But the point is the decrease significant enough as compared to the addition of one extra variable? If it is, on an overall, this will increase. If the new incoming variable is not significantly capturing more variability and decreasing SSE, then the adjust R squared will decrease. So again, going back to these two models, R squared adjusted for model A, and you have R squared adjusted for model B. What you will do is, if R squared adjusted for B greater than or equal to R squared adjusted for A, go with, sorry, if it is greater than R squared adjusted of A, go with model B. It is worth adding that extra variable. Else, if R squared adjusted for model B is less than or equal to R squared adjusted for model A, then go with model A, because the simpler model is the better model. You are not getting any significant impact. It is almost same. Model A and model B are almost same, or model B is worse than model A. In both cases, go with model A, which is simpler. Right? So that is the use of R squared and adjusted R squared. It tells you when to choose a variable to add, when to not choose a variable to add. And it is this concept that is extensively used in identifying which variables to keep in a model. When you use stepwise regression or subset method, all of that you learn in your ML courses, it is basically this concept. Which variables to keep, which variables to drop. Yeah. So this is what I have in regression that I want to touch upon. I did wanted to demo all of these with data with an Excel, but we don't have sufficient time. So I will stop here. Next week, from next week, Dr. Swaminathan will come and he will start handling logistic regression, which is week 7 content. Okay. So with this, we conclude the discussion of week 5 and week 6.
So from week 7, sir, Swaminathan sir will
Swaminathan sir will come. Yeah.
Okay. Good. Thank you, sir.
All right. Okay. In case if you have any questions, please feel free to ask. If not, we have 7 people on the call. Once it drops down to, let's say, 3, I will also close the session for today.